Okay, so we can now find the terms for big R. So remember, big R was defined as chi over rho, and rho itself was defined as alpha little r. Okay, so here's your chi. Your chi is sine of rho, and rho is alpha little r, and r is chi over r is chi over rho, and rho is alpha r. So anyway, here's your expression for r, big R. Okay, and that's in the case when that's for L is 0. Okay, so R0 is this. All right. Now, if you know the chi, you can find the big R. All right. Now, if you know chi 0, you can find chi 1 from the trick in previous session. So, if you can find chi 1, you can find R1, and if you can find chi 1, you can find chi 2, and hence you can find big R2, and so on. So again, I asked you as homework to actually calculate R1 and R2. Right? Now, general comment. I'm wondering, sometimes I wonder if I'm being fair. See, my initial plan was to aim at the alphas. My longer term goal is to teach alphas. Alphas being, of course, people in the top percentile, IQ percentile, in the top 1% of intelligence, measured intelligence. So, therefore, people of that level, they could solve this kind of stuff without too much problem. But I'm wondering if I'm being fair, because I wonder what percentage of you guys watching are alphas, are future students of graduate level, masters and PhD level, pure mathematics. I mean, it's quite possible, if I think about it, that the audience, you guys, the mix of alphas and non-alphas studying this stuff may change as the level gets higher. I mean, that's very plausible. I mean, it's quite possible that people who would be interested in the higher level stuff are not interested in this stuff because they already know it's too easy or something. And on the other hand, others of you may be very interested in this kind of stuff, have no intention of doing the higher stuff because too difficult or for whatever reason. But if you're not alphas, then you may object to me throwing all this homework at you. So I do wonder sometimes. See, I don't know right now what the mix is between alphas and non-alphas following this course at the moment. So maybe you can compromise to some extent. But anyway, if I spell everything out, it'll take twice as long. So I'm forced, just for practical reasons, in terms of upload time to YouTube and all that kind of stuff, to leave a lot of the working between the lines, so to speak, solving derivations and stuff, up to you. Anyway, but I do have question marks about it. All right, so solve the first few values of r's for given l's. Right? So you get increasingly complicated expressions, as you can imagine. All right, now we can start talking about boundary conditions. Like remember, the previous session we had a spherical, infinite spherical world, what we call it. Where the potential was 0 inside the sphere of radius little a, and was infinite outside that radius. So that means at the radius, you know, when little r is a, the wave function, or the r, big R in this case, has to be 0, right? And so for this to be 0, this is in the case little l is 0, right? Little l 0 here. So for that to go 0 when this is a, so you put an a here, so that means that alpha a must be n pi, right? Because sine of n pi is 0. So your n integers, you know, n can be, you know, 1, 2, 3, whatever, right? Now, okay, so you've got conditions now on your n, well, effectively your alpha. This, you know, this little equation here allows you to calculate the E, right, your eigenvalues. Why is that? Well, because alpha will then equal n pi over a, right? But what is alpha? Well, from the previous session we defined alpha to be the square root of 2 mu e over h bar squared, right? So if you square alpha, so you get n squared pi squared over a squared, n squared pi squared over a squared, n squared pi squared over a squared, and now we're trying to find e, so from alpha squared you've got an h bar squared underneath, so bring that over, it goes on top, and the 2 mu goes underneath, right? So that expression comes, that's your E, that's your eigenvalue, the energy. So we know the energy. So we've got an eigenvalue solution, right? Now, interestingly, that's the same eigenvalue for the odd parity 1D case energy eigenvalue, right? Now we can normalize the thing for the wave function. For R, you know, it's not too hard, just yeah, maybe. What are we doing? N is 1, okay, L is 0. So it's just, okay, so we've got a value for alpha. So again, you know, do that also for homework. This is your normalization term. So that, let's see, how would you... So this all squared, your integral, the volume, the d tau, the volume, you're integrating over the volume of the sphere, right? And you want that to be 1. The particle has to be somewhere in that sphere, okay? And you'll find the normalization factor will be this. So you do that also for homework, right? Now, you know, double bar, so sort of new thought. Now for the more complicated case, when L is greater than 0, so here we're assuming the simplest case when L is 0, but for higher, you know, when L is greater than 0, this boundary condition, it has to be 0, because outside the sphere the potential is infinite, right? So you can't have any wave function there. The wave function has to be strictly 0. There's just no probability of finding the particle outside the sphere because of the infinite potential. Okay, so this is true for any L. Okay, so solving for the energy, you know, the eigenvalues E is going to be more complicated because, you know, you're going to be using these kinds of, you know, functions. That's going to be tougher. And the textbook does not go into that. I guess, you know, more complicated stuff. You know, try it yourself if you like. I didn't. Right. So if your E goes large, the textbook just gives you some clues if you do want to go into this yourself. For all cases, you know, in other words, for all values of L, then as your energy gets large, you get these kinds of conditions cropping up. So for large energy, then your energy levels, or large energy levels, approximate, converge, if you like, to the energy levels in the 1D case. That's a bit of a footnote. All right, now hydrogen atom. So we can go back to that topic now that we've got theory of angular momentum under our belt. Done some more of the theory of the central potential. Then we can take the equation, the star circle. Which equation was that? Okay, that was the Schrödinger equation with the R and the L, right? And it was 2 sessions back. So it just had a general potential V in it. Okay, but now we're talking about the hydrogen atom. So we know what this potential is. We have a term for it. It's just the Coulomb potential here, right? So E is just the charge in the electron. R is the distance between the proton, in other words, the nucleus, because a hydrogen nucleus is a proton. Okay, so this R here is the distance between